In this video, we're going to cover the general form of a circular function. We're going to cover what are all the key properties of circular functions, as well as what are all the ways in which we can change the shape of the function. Let's get to it. The general form of a circular function is as follows. Each of the terms in this equation modify the shape of the graph in a unique way. This is the basic plot of sin x. Let's have a look at how each of the terms affect its shape. The a term is known as a dilation factor along the y-axis. All this means is that we're going to take the graph of sin x and just stretch it along the y-axis. This term serves another purpose. It is also used in calculating the amplitude of a circular function. The amplitude is the distance between the mid-level of a circular function and its peak. By this definition of the amplitude, it must always be positive a, even if there's a minus sign applied to the term. This is because when you apply a minus sign to the circular function, all it does is flip the graph. The distance between the mid-level and the peak is still the same, still positive a. I'm stressing this point in particular because this understanding of the amplitude is actually tested on your exam. In fact, it was tested in the 2023 Tech Active exam as a multi-choice question. Anyways, back to the plot of sin x. Sin x has an amplitude of 1. This is because the a term is implicit. We usually leave off the term if it is just 1 because anything multiplied by 1 is just itself. Now let's look at 3 sin x on the same axes. We can see that the amplitude is 3 times larger. That is, the distance between the mid-level and the peak is now 3. Notice how both plots have the same basic shape and they still intercept the x-axis at the same point? That all changes when we modify the n term. The n term is also a dilation factor, but this time we're stretching along the x-axis instead of the y-axis. This n term is also used in calculating the period of a circular function. The period tells us how long it takes for a circular function to complete one cycle. That's from peak to peak or trough to trough. It doesn't matter what your reference point is, it's just how long it takes to complete one cycle. The period is found using this equation, t equals 2 pi divided by n. If we look at the graph of sin x, we can see that n must be 1. Just like with the a term, if there is no explicit n term, we must assume that it is 1, because again, anything multiplied by 1 is just itself. If n equals 1, then the period must be 2 pi. And sure enough, we can see that a full cycle is completed in 2 pi. Now, let's look at sine 2x. In this case, the period is 2 pi divided by 2, which just simplifies to pi. And sure enough, if we have a look at this graph, we can see that now a full cycle is completed in pi. In math methods, most of the time you'll be asked to find the period of a circular function. But in the real world, and if you're studying physics, you'll often be asked to find the frequency of a circular function. The frequency is just the reciprocal of the period. That just means 1 divided by the period. The c term is the vertical translation of a circular function. You can think of this like setting the mid-level of the circular function. For example, our graph of sin x has a vertical translation of 0. This is because the c term is absent. This is a little bit different to what a and n were. A and n were dilation factors. They were multiplying the function in a certain way. C term is just an addition to the function. So if the c term is absent, it means it must be 0. And we can even read this off the graph. Again, the c term gives us the mid-level. And if you look at the graph of sin x, you can see that the mid-level is 0. But if we set a vertical translation of 1, say sin x plus 1, then the whole graph shifts up by 1 unit. Notice how the circular function is still symmetrical about the mid-level. Instead of oscillating between plus 1 and minus 1, we're now oscillating between 2 and 0. Finally, we have b, the horizontal translation term. b just shifts the graph left or right. The graph of sin x has no horizontal translation. This is because the b term is absent. Again, this is a subtraction, not a multiplication. So if the b term is absent, we assume it has to be 0. But if we set a horizontal translation of pi on 2, we can see that the whole graph shifts to the right, pi on 2. Remember, the general form of a circular function has minus b, not plus b. b is still pi on 2, it's just that we happen to be subtracting it rather than adding it. If b is negative pi on 2, then we should expect a translation lift. What we see is when we substitute negative pi on 2 into the equation, the minus signs will cancel out and it will look like a plus. Try not to get thrown by that. So, how do all these terms play together? Well, we've already explored how each term impacts the graph in its own unique way. This means that no matter what combination of terms we have, as long as the graph is in its general form, we can be certain as to what the graph will look like. Starting with sin x, let's change the amplitude from 1 to 2. Now, let's shift the graph up by 1 and to the right by pi on 2. We can finish up by halving the period. Hang on a minute, what happened there? The period was halved, yeah, but it also shifted the graph to the left a little bit. Actually, it shifted it by exactly pi on 4. What's going on there? Well, the problem is we didn't actually write this in the general form. The n term needs to apply both to the x and to the horizontal translation factor. If we do this correctly, we can see that the period halves and we also maintain our horizontal translation of pi on 2. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.